All right, so last time we introduced the concept of position, displacement, and distance. So, and also in this room, sorry, it's weird. In this room, by convention, I'm going to call walking to your right positive x, to the left to be negative x, and I'm going to choose something in the middle to be 0. So just I'm imagining there's this, I'm basically in my mind's eye superimposing a coordinate system on top of the room, which is physical, and I'm going to mark a special point called the origin. None of that's a mental construct though. Okay, so for other problems, you may not want to do it the same way. That's how I would do it. Okay, so then we talked about so position. So you can have I'm imagining I've got this real line. Sorry, I'm just trying to make sure it's all sort of visible. And we mark out a point, which is the origin. I usually will call that the x direction. Okay, so that was fine. Just marks out positions. And then we talked about the ability to change your position. I had two concepts that sort of both get at that same basic information. What were those called? I already used the words today. What were quantities which somehow were associated with changes in position? Distance and displacement. So they were, there is a little bit of similarity, but they're different. One of them is a vector and one of them is a scalar. Which one is the vector quantity? Displacement. Displacement is going to be the vector quantity. It's going to be the one we use almost all the time. And then we also have distance, which is going to be a scalar quantity. It's not as directly useful for us. Kind of after the fact, you could rewrite your equations that way using that variable sometimes, but it's not the most convenient one. Unfortunately for us, in our everyday language, we tend to use distance a lot. And when we think about things, sometimes we think about distance. So you have to you have to train yourself to be careful and not just slip into everyday language. We're going to use technical language, right? All right. So, imagine I start at, let's start very simple. So let's say we start here at the origin, and then we walk over to the position 2 meters. That is a displacement. So the symbol we write for that, or what it really is the change in position. Change in position. And because there's a difference between taking 2 steps, 1, 2, to the right, versus 2 steps to the left, 1, 2, those are different motions physically, and we want to preserve that distinction, then this is a vector quantity. The orientation matters. Because of that, to remind myself, I'm going to put an arrow over the top to remind myself that it's a vector. The arrow doesn't really do anything for me mathematically. It's just, at this point, it's really just a reminder. For this motion here, the way I should write this, if I'm being really careful, displacement, change in position. So if it's a change in position, that means it's going to be x final minus x initial. When it's initial, I put a subscript 0. Sometimes I'll say x initial, or I'll call it x naught, meaning time 0. If if I'm being really careful, just to be completely consistent, this is a vector and it goes in the x direction, so it should come proportional to the x unit vector. If I'm being really careful, it should be there. However, when we're talking about motion along one dimension, you don't have to worry about keeping track about x, the difference between x and y, because there is no y, in which case, a lot of times I will just drop the unit vector, because there's no ambiguity. If you're only moving in the x direction, everything has a unit vector x hat, and it's fine. When we have two dimensions, then you really have to keep track. So I'm going to drop this, basically, now. It really should be there, but I don't want to clutter things unnecessarily. We'll have plenty of fun with unit vectors later. So for right now, let's focus on this, because this is the key new stuff. Make sure I'm on the screen. All right, so we have that. So change in position. Final position minus initial position. Okay? On the other hand, we had distance. How did I define distance? Yeah. So, right. Yeah, I gave a physical definition. You can probably jazz it up. But since we aren't going to use distance, I'm not going to waste time making it super fancy. This is it. I mean, however you mathematize it, it'll be this. Okay? So basically, what I imagine is that I've got this thread, and I just, as I walk, I spool it out. And then if I change directions, I just keep spooling it out more and more and more. And when all is said and done, I measure the length of the thread. That's distance. So, and it's a scalar, because whether I was going forwards or backwards, when the distance just kept growing, it didn't know about the orientation of my motion. So this is the length of thread needed to cover your path. I just keep accumulating markers in my pockets. It's almost like Santa's toy bag or something. It's like or Mary Poppins' carpet bag, except it's markers. So this is the length of thread to cover your path. And it just keeps growing. So you can see displacement has a subtraction involved, so you can get cancellations. Whereas distance, it just keeps growing, 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 growing. All right. Okay, so that was, we did a couple of examples. Now for this path right here, when I started at the origin, indicating, okay, step 2 times to the right, what would be the displacement? Well, we identify the final position, 2. We identify the initial position, 0. I just plug it in. 2 minus 0 is 2. And technically there should be a unit vector there, but we're going to not get distracted by that. So 2 meters. What about the length of thread needed to cover this path? It also would be 2, but it's 2 kind of for a different reason, right? Because it's a different quantity. Right? You can really see the difference between distance and displacement by considering the following path. Imagine you start at -1, you go all the way up to 1, 2, 3, change direction and go back to the origin. So if you have this sort of change of direction, that's really going to highlight the difference between these concepts. So displacement, it's just always this. In my mind, sometimes I think of it as, it's kind of like from where you started to where you end, kind of the path as the crow flies. We have the, that's the phrase. You guys use that phrase. So, but anyways, so the initial position would be -1. The final position would be 0. So it would be 0 minus -1 plus 1. Because the displacement, delta x, I can think of it as a vector from start to finish. It's plus 1 meter. Okay. The distance, though, would be the length of thread to cover that path. So if I started here, to cover that path, I would need 1, 2, 3, 4, go backwards, 5, 6, 7 meters of thread. And there's that just clearly shows the difference between them. All right. Great. So we can, so that's just a review of what we did last time. What I would like to do now is think about these changes in position as happening over intervals of time. So it's the same concepts, we're just going to repackage it. And one way I might try to do that is I can make a graph of my position over time. So this could be your position x over time. I don't know. It could be whatever. You could say at time 0, we have some initial position, and then it could be a straight line, for example. Actually, well, let me not do a straight line. It could be any path, right? So what this would mean is at the beginning, if I mark out 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, what this would mean is over the first second, my position changed by just a little bit because the height just changed by a small amount. So that would be, in the first second, I just went a little bit. And then from seconds 1 to 2, my height changed a little bit more. Which isn't visible at all. I don't know what I can do about it if it's not, but not very visible. All right, try to make these thicker. All right. From 2 seconds to 3 seconds, I had an even bigger change in position. And then from 3 to 4, bigger. Okay. So the change in these level curves, change in the heights, that would give you a displacement between different moments in time. So that's how you should think of it. All right. Okay, so while we talked about this, rates of changes of graphs, we're going to do that all the time. We're just going to give it a name. The key concept here is the concept of velocity. Morally speaking, we'll be technical here in a minute, but morally the concept is velocity is capturing the time rate of change in position. So the time rate of change in position. That's just kind of morally true. So in particular though, we talked about, I think on the first day and even the second day, two kinds of rates of change. We had an average rate of change, and we had an instantaneous rate of change. Okay? The average rate of change is the slope of the secant line. Okay, So if I had, let's say I wanted to know the average rate of change from 1 second to 1, 2, 3 seconds. The average rate of change I hope it's still recording. Sorry, Chad. It's probably pretty rough. All right, we're going to define the average velocity to be the slope of the secant line over a time interval. In particular, then, the average, it's going to be a vector quantity. It's going to be the change in position over the change in time, or the change in displacement, or the displacement over time. Okay? So that is the average velocity. The other notion of rate of change we had was instantaneous rate of change. So that would mean you go to, you kind of zoom in, you take a limit, and you focus in on one point. And then you focus on the slope of the line that is tangent to the curve at that one point, and find its slope. What process have we talked about that gives instantaneous rates of change? I've practiced it a whole bunch. What do we call that? Derivative. Okay. So the other notion of velocity is going to be, and I'm just going to call that V. I'm not going to write instantaneous because normally when we talk about velocity, we mean the instantaneous velocity. The average one is, sometimes we use it as an approximation. We don't really use it all the time, or most of the time, right? That is going to be dx dt. Okay? So what does this mean? The velocity then is capturing the idea of per second, going forward in time, how much position are you gaining or losing? So if you have a positive velocity, every second I'm gaining position. I'm moving to the right. On the other hand, if I have a negative velocity, that means every second I'm losing position. I'm moving to the left. Notice, my position could be positive, but my velocity could be negative at the same moment. Because I could be standing with a positive position, but losing it over time. Not like going crazy, but I mean, like every second, it's becoming less positive. That's a loss of position, right? So the signs of this don't tell you where you are, they tell you where you're going that way. It tells you about changes in position. Okay? All right. We use these concepts all the time. And when we think about the world, we get in the car. Why do I press the accelerator? To achieve some velocity, to make motion happen, right? So these concepts are clearly relevant to describe the world. But this isn't usually the language we use. What language or what word do we usually use to describe motion over time in everyday language? Speed. And your car has a speedometer. Not a velocimeter, I don't know. We don't have that. We have speedometer. Speed is connected to velocity, but it's not the same. In fact, it's kind of very analogous to the difference between displacement and distance. Speed is going to be a scalar quantity. Velocity is a vector quantity. We will use the vector quantities much more often than the scalar ones. one way to see that your speedometer, or that speed is a scalar quantity, is in your car, you hit the accelerator, you gain speed, okay, so you're going down the highway, it reads 60 miles an hour, or 100 kilometers an hour. That's all it tells you. It doesn't tell you whether you're going north, south, east, west, vertically, hovercraft or something, I don't know, right? It's telling you one number, and it does not convey any information about orientation. That speed number is a scalar, okay? Okay, again, we're gonna have two kinds of speed, actually. We're gonna have an average speed, and then we're gonna have an instantaneous speed. The average speed, make sure I'm on the screen, is the total distance traveled over the time it took to travel it. So that would be the distance over the change in time. Right? We also have a notion of speed right now. Right? That's actually what your speedometer is telling you. At each moment in time, there's one speed. It's not like if I'm traveling for 7 hours, I don't really care that my average speed was whatever. I want to know right now. Okay? And for that, we have the instantaneous speed. We just call that speed, usually, without saying instantaneous. And that is the magnitude of the instantaneous velocity. And right now, magnitude, if you're in one dimension, magnitude means just throw out all the minus signs. When we get to other cases, it means Pythagorean theorem. If you have a vector that goes in 2D, you find the length of the hypotenuse if you draw it as a triangle. Okay? So, that's what it means. All right. So, let's go through some examples to highlight these. All right. Forward here. So let's imagine, I don't know why, I'm not going to explain why this is the case. I'm going to give you a graph of position versus time, and I'm going to ask you to calculate various quantities from that. Okay? So, let's take time. We'll say that's 1, 2, 3, 4 seconds, and we'll say it's 1, 2, 3 meters. And let's start really nice. So let's say that this is a graph of let's say that the position graph x equals 2. We need to think about units here. Times time minus 1. We need to think about units here. I forgot to discuss units. Velocity and speed, the rates of change in length over time, so they have units of length over time. So for us, we're going to have meters per second for velocity and position as units of meters. Okay, so anyway, so this equation now makes sense unit-wise. I would like for you to graph this curve. I would like for you to find the average between 0 and 4 seconds. Find V instantaneous at t equals 1 second. Find the, let's see here. Let's find the distance between 0 and 4 seconds. Think about that for a little bit. And then find the average and instantaneous speeds. Oh, sorry. Okay, so there are 5 tasks there. Tilt this a little bit more visible. 5 tasks there. Take a second on your page and try to complete them. It should be pretty simple. There are 6 tasks because you're supposed to also reconstruct this graph. Okay. Take a second and work it out. Chad, I will tilt this up so you can hear the definitions. They're up above. Take a second and write those down, then I'll tilt it back to the problem on the board. I'm trying to choose something that's really simple so it's easy to apply these formulas. Who thinks they have the graph? Good. Anybody doesn't have the graph? Okay, it says they have the graph. All right, so I'm going to slide this up and I will draw the graph. So my graph, so my equation is x equals 2 meters per second times t minus 1 meter. So this is a linear function in time. So it's not too bad to graph. 1, 2, 3, 4. 1, 2, 3, 1, 2. All right. So I start down here at when time is 0, I have a position of -1, because that's my vertical intercept. So that's actually what I will usually write as x0, x0, the position at time 0. And then I have this curve. Oh, I didn't give myself enough room. Top flight board work right there. Try that again. 1, 2, 3, 4 for time. -1 for x0. 1, 2, 3, 4, 5, 6. It's close, won't quite fit. All right. Now, at time 0, it's down here at -1. That's visible. And then I need a line whose slope, set the units aside for a moment, the slope should be 2. Okay, so that means I go over 1, up 2. Over 1, up 2. Over 1, up 2. Over 1. Well, all right. So I should be all the way up. After 4 seconds, it should be up at a height of 7, which I didn't have there. So this is, I'm out of room. This is at x of 4 seconds equals 7 meters. Okay? So everyone should have that graph. Apologize for my poor artwork. Okay. The first task was to find the average velocity between 0 and 4 seconds. So the way you would do that is change in time over 4 seconds. So that's going to be x final minus x initial divided by the time final minus time initial, which is 0. Because I went from 0 to 4 seconds. This is simply going to be 7 meters minus -1 meter over 4 seconds minus 0 seconds. Notice, I'm not afraid of minus signs. The formula is what it is. I plug in whatever I've got, positive, negative, yeah, I'm not afraid of minus signs. So if that means I have to subtract a negative, so be it. It just is what it is. This gives me 7 minus -1, that's 7 plus 1, it's 8, so that's going to be 2 meters per second. Okay? Was everybody able to unpack the definitions to see that, how it worked out? Okay? How about the instantaneous velocity at time equals 1 second? Well, I need to take a derivative. So here's my, that's dx dt. So that's going to be the derivative acting on this expression. 2 meters per second times t minus 1 meter. Take the derivative. This 2, I know it has units, but it's a constant. It passes through the derivative, there's no effect. So the derivative only hits the time here. And then, I should have also said, the derivative of the sum is the sum of derivatives. When I take the derivative of -1 meter, that's 0 because it's constant. So this, in fact, is nothing other than 2 meters per second. And when I take the derivative of t with respect to t, you get 1. So there's no effect. Oh, whoa. Why is it that the average velocity is the same as the instantaneous velocity? It's a line, right? I told you this is the simplest thing you could do. I'm working through the definitions on something simple and then we'll jazz it up. Okay? That is not normally true. It's just because this was a line. And one of the defining properties of a line is that the slope is constant. So that means that the derivative is going to be the same as the average slope. Awesome. But generally that won't be the case. The average speed. Well, this one's particularly easy because there's no change in direction. And so the distance traveled is actually going to be the same as the displacement. If you have changes in direction, we saw that there are minus sign issues. But here it's nice. So for us, the distance traveled is 8, because that was our displacement. And then the average speed is going to be 8 divided by 2. It'll be the same. And finally, we have the speed at 1 second. What was the definition of the instantaneous speed? The instantaneous speed is the magnitude of the instantaneous velocity. So if there's a question about instantaneous speed, it's actually secretly a question about velocity, then find the speed. So in this case, it's that, I mean, the magnitude of it, but because it's positive, it's the same. The instantaneous speed was positive 2 meters per second, so the instantaneous speed is 2 meters per second. Oh. All right, so these were all the same because it was a positively sloped line. Any other, basically anything else won't. They won't all be the same, they'll all be different. Okay? They're all capturing, morally speaking, kind of connected pieces of information, but they are different. All right. Let's try one that's a little bit more complicated now. What if I gave you, let's say that I'm going to give you this thing. X equals X equals minus 2 meters per second squared. I need that to get the units right. Times t squared. Okay. This one, yeah, give me, so I want you to sketch this from 0 to 2 seconds. I want to know the average velocity from 0 to 2 seconds. I want to know the instantaneous velocity at t equals 0 seconds, t equals 1 second, and t equals 2 seconds. Okay. I want to find the average speed from 0 to 2 seconds, and I want to find the instantaneous speeds at each of these. At time equals 0 seconds, 1 second, and 2 seconds. Okay. So take a second. Try to work your way through that laundry list of tasks. want to circle around and see. Yep. So to make that sketch, you could just plot points, and you kind of know the form because it's what kind of graph isn't it? What do we call that graph? No, exponential would have constant, would have base, have variables. It's quadratic. It's a parabola. So we know what parabolas look like. So you just plot the points and just kind of smooth it out. Just plug in time, what you get for time equals 0, time equals 1. That just makes it. So you gotta, okay. So redraw it. Redraw it. Redraw it. Here's what I'll say. This part is really simple. You don't want to waste brain cells doing it and reinventing it each time. So do it the same way each time. There will be enough enough fun for us to have that we don't want to make things even more fun by drawing our axes in weird ways. Okay. Yep. Good. Okay. Now. That's fine. All right. Shapes of things to kind of. All right. So going around the room, we're doing okay. I'm gonna do my solution up here. Okay, so I make my graph of time, and I said 0 to 2 seconds. So I'm going to focus on 1, 2. This is x. At time 0, I plug in t equals t equals 0, and my equation, I'll write it here so it's in the screen. Was that x equals minus 2 meters per second squared t squared. So if I plug in time equals 0, I just get 0. And I see that the initial height, x0, is 0. And then I plug in, okay, I put in 1 second. So that gives me minus 2 times 1. It's going to be negative 2. And then I plug in 2 seconds, and I'm going to get negative 2 times 4. Oh, I better keep going. So I need to go down to negative 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm like way down here. Furthermore, this is kind of a pretty simple parabola. You don't have the linear or constant terms. So what does that look like at the origin? Does anybody know? Does it have a slope? Is it tilted at the origin, or is it flat? Like it's the origin. It's flat. So it should look like the, it's so bad. I'm sorry. All right, it should be flat and go down. I'll just move my point over and see. I can cheat. And then we get down to here. Okay, so it's a parabola. It should look something like that. Sorry for the art. Okay, let's go through, so that's my sketch. I'm never gonna grade someone on their artistic abilities. I guess I gotta go one more. It's gotta go all the way down to, this should be at -8 meters for x of 2 seconds. So at 2 seconds, it's at -8. Okay, one comment. I should have mentioned this before. Notice, you don't have to do this, but I think it's advisable. When I write algebraic, all right, who knows how this video is going to be. All right, so the average velocity is the change in distance. No, you tricked me. Not the change in distance over change in time.
Change in displacement?
Change in displacement. It's the change in position over time, not distance. If you say it the wrong way, then it kind of wiggles its way into your brain, and it'll be wrong. Okay? It's the change in position over time, or the displacement over time. Okay. So the average velocity is the change in position over time. So that's going to be delta x over delta t. All right? From 0 to 2 seconds. So this is going to be the final position, -8 meters, minus the initial position, 0 meters, divided by the time, which is 2 seconds minus 0 seconds. So I get an average velocity of -4 meters per second. Yeah, still on the screen. Okay, -4 meters per second. How many people had that result? Great. How about the instantaneous velocity? How do you do that? Well, what I would do is I would do the calculus first with letters, and then after the fact plug in different time values. There's no point in taking the derivative 3 times. Do the derivative once, and then evaluate it 3 times. Okay? So that is simply going to be the derivative of position with respect to time. Okay. Well, I have my formula here, -2 meters per second squared, t squared. The stuff out front is a constant, so it doesn't play a role. It just floats through. Right? Just don't forget to write it. And then I have to take the derivative of t squared. That's not hard. We've been doing way harder stuff. What's the derivative of t squared with respect to t?
2t.
2t. The old exponent is 2. You lower it by 1. So I end up with -4 meters per second squared times t. How many people had that expression? Okay, good. And now I plug in values. So at t equals 0, I get that v equals 0. At t t equals 1 second, I get v equals -4 meters per second squared times 1 second. The units clean up, and I get -4 meters per second. Okay. And then what about t equals 2 seconds? Well, that's going to tell me that the velocity at 2 seconds is -4 meters per second squared times 2 seconds, otherwise known as -8 meters per second. That's all visible. Yes? Okay, good. I'm sadly starting to note the fact that I'm getting older, because first semester I did Zoom stuff. I could clearly read what was on the screen, and now I can't. It'll happen to you guys too. Just wait. Okay, how many people had these instantaneous velocities? Okay, if you didn't, do you see how I got them? Is that all right? Just trying to be clear. All right. Let's go through and find the average speed. That's simply going to be the distance traveled over the time. What was the distance traveled from 0 to 2 seconds?
8 meters.
Positive 8 meters. Distance is never negative. So the distance is 8 meters. The times was 2 seconds. So the average speed would simply be 8 meters over 2 seconds equals +4 meters per second. And that's a scalar quantity, no direction. As far as the average, or sorry, the instantaneous speed at those 3 times, the way we do that is we take the magnitude of the instantaneous velocity, and so in one dimension that just amounts to dropping minus signs. So at t equals 0, we get 0 meters per second. T equals 1 second, we get 4 meters per second. And t equals 2 seconds, we get 8 meters per second. Okay? Now, so this example kind of shows all the differences between things. In general, when you have wiggly motions, wiggly position graphs, all these numbers are different, and you have to work through, and you really have to go through all the definitions of things to figure stuff out. You can't just calculate the instantaneous velocity and just assume that that's the same as the average velocity, or vice versa. You really have to go through and think it through. Okay. Are there questions on this? Feel okay? All right. We're going to do our lab. I handed it out last time. I've got it. And it's on moving and walking around in front of motion detectors, basically reconstructing the graphs of position and velocity. Right? So it's just trying to make these motions physical to you. Right? So for Chad, I will stop the video, and then when you are feeling up to it, or we'll figure out what we need for you to do. All right.